In 9.7, we're going to look at how to solve systems with quadratic equations. So there are three cases here. You're going to have one with no solution, one with one solution, and the other with two solutions. We're going to use the method of substitution to solve quadratic equations for now. So for the first example here, I'm going to take this first quadratic equation, 2x squared plus x minus 1. I'm going to set it equal to the linear equation, negative x minus 3. So basically, I substituted in y for this y, or you can look at the other way around. And now I am going to rearrange all these terms to one side, with the left-hand side to be exact. So this will be 2x squared plus 2x plus 2, and this will be equal to 0. And now I can simplify this equation further. So we get x squared plus x plus 1 equal to 0. As you can see, we can't factor this, so I'm going to use the quadratic equation to see what I get. So my b is 1, so I'm going to square that, which is still 1. 4ac, these are all 1s. Well, I'm going to stop here and look at the discriminant. And this happens to be less than 0. So I can conclude that in this case there are no real solutions for this system. Now let's look at a case when there's only one solution. So I'm going to substitute this 2 in for y. And I'm going to, again, move everything to one side of the equation because I'm going to try to see if I can factor this to solve. And I could change all of this to positive. I can simplify. And I see that I can factor. This is a perfect square trinomial. You can use any method to solve for the x. I'm just choosing the way that I think will be easiest. And then now x would equal to negative 1. And I only have one solution here. And now when x is negative 1, y must be 2. And I could check it with the first quadratic equation here. Y equals negative 2. 1 squared minus 4 negative 1. 2 plus 4 equals 2. So your solution is only negative 1, 2. Okay, now let's look at the case when there's two solutions. Again, I'm going to set these systems equal to each other by substitution. So this quadratic equation is equal to the linear function 2x minus 4. We rewrite this in quadratic form. This will be minus 6x plus 5. And I see that I can factor. So that's the first thing I'm going to do. This is the quickest. 1, 5. So I have two solutions of x. So I need to look for two coordinate points. So I'm going to take the linear function, which is easier. So when x is 1, what's y? Y would be negative 2. So I have 1, negative 2. And the second one, 5. So this will be 25 minus 20, 5 plus 1, 6. It will be 5, 6. And here are your solutions. Your textbook has a type of problem where it wants you to solve the equation using a system. Well, now looking at this is y. This is also another y. So basically, I could label this y1, y2, and this is a system. So to solve this, you're still using the same method as before. So we would like to rearrange this so that it is in quadratic standard form. So this would be negative x squared, negative 2x plus 3 equal to 0. So basically I moved all of these over to the left-hand side of the quadratic equation. Now I would like to factor the negative out. And I see that I can continue to factor this. And I notice that I have two solutions, x equals to negative 3 and 1. Well, earlier I told you that this is one of the systems, so I'm going to use this system because it's easier. So I'm going to say y2 equals negative 2x minus 1, and I want to find out what my y value is. Okay. So negative 2, negative 3 minus 1, 6 minus 1 is 5. So one of my solutions is negative 3, 5. And the other one, negative 2, 1 minus 1, so this would be negative 3. So my other solution is 1, negative 3. Now in this case you have a system of two quadratic functions. Okay, let's first solve this. To simplify this, so this would be y equals 2x squared, and then I can say y over 2 equals x squared. Okay, now I can substitute x squared for y over 2. Multiply both sides by 2. Then y equals 16. Now I'm not done here. I'm going to take the first equation, well, we'll just use y equals 2x squared because I simplify that. I'm going to substitute y for 16. I need to solve for x. X squared will be equal to 8, and here I need to use square roots to solve. So this would be positive negative 2 square root of 2. So then I can conclude that when y is 16, I have two roots, or two solutions of x. So my first solution would be negative 2 square root of 2, 16. And my second solution would be 2 square root of 2, 16. And if you sketch the graph, it should look something about like this. So y equals 2x squared, and then x squared minus 8 equal to 0. So our zeros would be at positive negative 2 square root of 2. So it's probably around here. And then we're treating this as y equals x squared minus 8. So it's going to be shifted down 8 units. So it will probably intersect, I'm sorry, this graph is not perfect, at these 2 points. Okay, and for this part, this is actually a very interesting problem. I'm going to first cancel out the ones, so I get 2 to the x power equal to 2 to the x. I'm going to rewrite this as a system, y equals 2 to the x, and y equals 2 to the x. And as you can see now, this is an exponential function that you have not learned yet. But I would like to touch on it a little bit for now by plotting points. So when x is 0, y is 1. When x is negative 1, y is 1/2. When x is 1, y is 2. Let's do one more. When x is 2, y is 4. So to go ahead and plot these points. 2, 2, 4. Now we're interested in where these two graphs intersect. So here we have, again, an exponential function that is shaped like this, and how to the right here we have a linear function. So we can, by logic, assume that this system must cross at 2 points. So when x is 0, y is 0. When x is 1, y is 2. When x is 2, y is 4. Now, look. We found 2 points. Now I'm ready to graph the line here. So 0, 0, 1, 2, 2, 4. So this is y equals 2x. This is y equals 2 to the x. So here we have two solutions. Here's solutions. 1, 2, and 2, 4. Okay, now let's look at this following system. This first one here is actually a graph of a circle. And the second one is actually the graph of a line. So we want to find their intersecting points. So by logic, we have a circle, and if they do intersect, they must intersect at 2 points. So you shouldn't have more than 2 answers for the system. So we have x squared plus y squared, and we could substitute this in for y. And now we can expand this binomial. So that would be positive x squared followed by 2x followed by plus 1 equal to 41. And then we have 2x squared plus 2x and then minus 40, which equals to 0. And then x squared plus x minus 20 equals to 0. And now you can factor. Okay, so x would equal to -5 and 4. Now I can find two solutions. When x is -5, y is 4. And when x is 4, y is -5. So you have two solutions. -5, 4, and 4, -5. 2 points. Okay, for this first word problem, I'm not going to ask you to solve anything. I just want you to understand the concept behind it. So during practice, you hit a baseball toward the gym. So basically, we have a gym here, which is 240 feet away. So according to the graph, this gym is 240 feet away from where the baseball was hit. The path of the baseball after it is hit can be modeled by the equation. Okay, so the graph is given to you right here. Okay, so the roof of the gym can be modeled by the equation y equals 2/3 x minus 1/20. So here we have this graph here. Okay, but we only want to account for this part of the graph for the roof. For values of x greater than 240. So like I said, we don't care about this part of the graph. and less than 320 feet. The wall of the gym can be modeled by the equation x equals 240. So it's talking about this wall here. This graph can be modeled as x equals 240 for values of y between 0 feet and 40 feet. So we want to cut it off at this point. Does the baseball hit the roof of the gym? Well, after the parabola is graphed, it intersects at this point, which is about between 220 feet and 240 feet. But it doesn't hit the roof because it doesn't intersect at the point 240, 40, or any point above it. So the answer is no. Okay, now let's look at this word problem. Toby is riding his bicycle in a large park following the path modeled by the equation. Cecile is also riding his bicycle in a park following a path modeled by this equation. Do their paths intersect? If so, what are the coordinates? Well, first we need to solve this system and check to see if they have a point of intersection. Okay, so this is a perfect square trinomial. So x is equal to 2. So there appears to be one solution for this case. So the intersecting point would be at 2, 9. Then we have the second problem here. Carmen's hat was blown off her head by a sudden gust of wind. So probably this is Carmen. And then her hat, maybe the wind was blowing, and her hat probably just went off like that. And the wind is pushing the hat away from Carmen, following a path that can be modeled by the equation y equals x squared plus 2. So this is somewhat like a parabolic path. And Carmen starts racing after this hat, following a path modeled by the equation y equals x plus 1, which is a linear function. Will Carmen be able to catch up to her hat? So let me first draw a sketch of this graph here. Now, the parent graph is y equals x squared, and I'm going to shift 2 units up. It will intersect the y-axis at 0, 2. And to draw this graph, we have y equals x, and then shift up to the y-intercept of 1. Now, we don't know if these points will eventually cross. Now we need to double check. And as you can see, you can't factor this. I'm going to double check with the quadratic formula. Or more like you can just double check the discriminant. Okay, and then this will come out to be 1 minus 4, which is negative 3, and that's less than 0. So in this case, there are no real solutions. So we can conclude that Carmen will not catch up. So this graph and this graph, they will never cross.